now records. It's recording, and let's share the screen, so the worksheet. Okay, can you see it?
Yes, now I do.
Okay, great. So, okay, so you can just like go, and if necessary, I'll like correct you with anything. So you can go like through questions.
Well, I just did this without the math because I had the information that the sun has a 2 times 10 raised to the 30.
Okay.
And you know, the mass of the sun was so overwhelming that for sure the only object that was important was the sun.
Okay, fine. But when you look at these numbers over here, it says interior mass. So basically what you're looking at Mercury and what's inside of Mercury's orbit. Inside of Mercury's orbit is just like sun. So it says that interior mass is one solar mass. And then when you go to Venus, right now, interior mass to Venus is going to be sun plus Mercury. And so if you follow that logic, you come to the last planet, which is Neptune. So what's inside of Neptune's orbit? It's like sun and 7 planets. How much change do you see over here compared to, you know, where you started?
Not much.
Not much, exactly. So initially you have one solar mass that's inside of Mercury's orbit. And then you come and you add all of the planets of masses of planets, and it's 1.0013, which means that, you know, is this like 1% difference? Did you add 1% of mass by the time you came to the last planet?
Yeah, that's what I was thinking. I look at that and I say, you know, if that, you know, more or less I was counting that the sun will be like 98%.
Mm-hmm.
So, you know, something more than 90, you know, 98.
I know.
Something more than 90. Then it's overwhelmingly, the only thing had to be the sun.
Okay, but now look over here. You have 1 and then 0.0013, which means actually you have 0 tenths and 0 hundredths, and 1% is 100. So that means that by the time you add all of the planet masses, right, you did not even add 1%. So the sun's mass is actually 99.99, right? I mean, that's what you're getting over here.
99.9. I was thinking something like 98.
No, it's not. It's actually 99 point, and then you can go like, I don't know, 8, 7, I guess.
Then in the second question, because you know, they just ask you agree with the first one, is first student or the second? I agree with the second student.
Good. Yes.
Reasoning, you know, the sun, they put here, the sun has the larger mass in the solar system and holds all the other objects in orbit and control their motion with its gravitational force.
Yes, okay. So student 2 is correct. Majority of the mass in the solar system is from just the sun by itself, because as we said, even when you add up all of the planets, you're adding less than 1% of the mass. So most of the mass is inside of the sun. Okay, how about question 3?
Planets close, I'm just gonna tell you, but planets closer to the sun speed faster, and planets farther from the sun speed slower. And this was related to the Kepler's second law.
Okay, Anna is here as well. Good.
Yeah, I'm sorry, I'm a little late.
Hi, Anna.
Hi, I didn't touch the worksheet. I actually just got done with the textbook, so I'm just gonna like.
Can you somehow make yourself talk like louder, because I can barely hear you?
Can you hear me right now? Can you hear me better?
I don't know. Try speaking.
Oh, okay, sorry. I was saying that I haven't gone through the worksheet yet, but I'm gonna go through it. But I wanted to know what question are you guys on, and then I'm gonna just work on some other problems.
Okay, are you happy with your exam score?
I actually didn't check it.
Oh, okay, good. More than 100%. Congratulations.
Again? Oh.
Yes.
Oh shoot. Okay.
Cool. Good. I'm very happy for you. Okay. So good. So Raush and I we are at the question number 3. So you can catch up if you want. So when you look at this table, then you're given all of these speeds, and you can see that Mercury moves fastest, basically. And then as you go further and further away from the sun, the planets move slower and slower. Do you know why that is?
Repeat the question one more time? Sorry, I think I knew the answer.
Yeah, so basically what I'm now asking is actually explained before question 4, right? So what do you have over here? Why do planets, as you look now further and further away from the sun, why would planets slow down?
Because there's less force on them.
Exactly. Exactly. So the point now over here is like exactly for this to click in your brain, that the speed of the planet in the solar system depends on the amount of the force of gravity that it feels. Now, the force of gravity depends on what?
Mass.
Mass of the sun, mass of the planet, and then what else?
The distance.
The distance. Okay, very good. So then the question 4, what is the answer?
Let's see.
So
Yeah. More distance, more gravitational force. Less distance, less gravitational force. More mass, more gravitational force. Less mass, less gravitational force. Then it's what you just said, distance and mass.
Okay, fine, but I don't agree about the distance. So more mass, sure, more force. But how about distance? If the planet is closer to the sun, so smaller distance, does it feel more force or less force?
more force. Or depends on the mass. I don't know.
Depends on the size, no?
Well, but as you said, most of
More force because you know the sun is big. It's a big team pulling a little team.
yes, exactly. You already said that most of the mass is going to be in the sun. So all of these differences by mass between planets, they're not even that important, right? Because 99.99 something of the mass is in the sun, right? So the sun is going to be that dominant mass contributor in the force of gravity. But how about distance? So far from the sun, those planets, do they feel less or more force?
Less.
Less, because gravity decreases, the force of gravity decreases as the distance squared, right? You double the distance, the force of gravity goes down 4 times. Remember that?
Yep, I remember.
Okay, good. Raujda, are you here?
Yes. That's,
okay. Okay, so let's now fill in the blanks. Anna, you wanna read this and fill just in blanks. This is very simple.
Okay, I'll read it.
Okay, who wants to go?
Oh, sorry, I didn't know.
Planets inside Neptune's orbit and 1 planet inside Mercury's orbit.
Okay, stop there. What 8 planets inside Neptune's orbit at what, and is there 1 planet inside Mercury's orbit?
I just count Mercury as the planet because the sun is not a planet. Mercury
yes, but so don't count. It's asking you inside of Mercury's orbit how many planets. There's 0 planets, right?
0, 7 on Neptune and 0 on Mercury.
Yes, so 7 planets inside Neptune's orbit and 0 planets inside Mercury's orbit. Okay.
We don't count the planets then.
I guess
okay.
So. We don't.
There are 7 inside Neptune and 0 on Mercury.
Mm-hmm.
And then, however, the interior mass of Neptune is approximately the same.
Yes?
The same as the interior mass of Mercury. Neptune is
okay.
About farther from the sun
Mm-hmm.
as Mercury.
Mm-hmm.
Therefore, the gravitational force exerted on Neptune is stronger.
Wait, Neptune you said is much...
Is weaker.
Weaker, okay, good.
Is weaker as the force exerted from Mercury. As a result, Neptune has an orbital speed that is much slower.
Okay, very good. Okay, that's it. So the force of gravity is related to the speed of an object. That's the idea over here. Okay, what do you say about this question 6?
Okay, let's see. Oh, that one is a guess. Okay. Which planet? I would think Jupiter because it's the bigger one. I put because it has more mass and is closer to the sun than the Saturn. That was like this.
Okay, fine. But if you, so which planet will experience an increase in gravitational force and an increase in orbital speed? So you say Jupiter, how about Saturn?
Well, I had Jupiter.
Okay, but so now go back at the beginning of the page and read over here this paragraph and just tell me if you change your mind. So you're saying now that Jupiter will move faster if you add this mass between Jupiter and Saturn. Now read this paragraph and just see.
Jupiter.
Yeah.
Hello?
I don't know. What do you think? What did you say?
Gravitational force also depends on the mass, and Jupiter is bigger.
I know, but that's not the point. What, like, once again, this highlighted sentence, what does it tell you? It states that the strength of the gravitational force depends on the amount of mass that it's inside of planet's orbit. So if you now, and also the distance, so if you add the mass between Jupiter and Saturn, is that mass inside of Jupiter's orbit or it's inside of Saturn's orbit?
Saturn's orbit.
So then, based on what you just learned, is only going to affect the speed of Saturn, right?
Yeah.
Hello?
The speed, I think.
Yes, because it is outside of Jupiter's orbit, so it does not really affect Jupiter. No, you're putting, it says you're able to add a very, very large amount of mass distributed evenly between orbits of Jupiter and Saturn. Which planets will experience an increase in gravitational force, an increase in orbital speed? Hmm?
Jupiter, Mars, Earth, Venus. Inside Saturn's orbit are Jupiter. Hello?
I don't agree. I'm waiting for Anna to get like into discussion.
I'm trying to talk. I mean, I am talking, and I
okay, now I can hear you. Okay.
Oh, you're not hearing me. That's why. Oh,
yes.
I'm sorry. I'm sick, so my voice is a little bit off. Sorry.
That's okay. Now I can hear you. So go ahead.
Yeah, no, I agree. You were saying that the mass is distributed evenly between Jupiter and Saturn, and that mass would be considered inside Saturn's orbit.
Mm-hmm.
And so, with that statement given about how the speed of it is determined by how much mass is from the center of that planet.
Mm-hmm.
Orbit and the distance, and so that would mean that one would have an increase in speed.
Saturn.
Yeah, Saturn.
Okay, and would it affect Jupiter at all?
That's a good. I think it would, but not as much as Jupiter.
Well, is it inside of Jupiter's orbit or it's outside?
Oh, I guess it's outside, so it would not affect it.
It would not affect it. Okay, yes, it would not affect it. So that's something to take away from here. Only the mass that's inside of the planet's orbit affects its speed and the gravity that it feels.
Orbit.
Okay, that was the answer?
Yes, so basically it says which planets will experience an increase in gravitational force. So Saturn for sure, and then the other two planets that are behind Saturn or farther away from the sun than Saturn.
Uranus and Neptune.
Yes.
Oh.
And the reasoning on this, what it is. Only
The reason for that it's stated over here, okay? The strength of the gravitational force depends on the amount of mass that it's inside of planet's orbit. So if you put it like behind Jupiter, it's not inside of its orbit, right? So Jupiter will not get affected by this added mass. It's not going to increase its speed, okay? But it's going to increase the speed of Saturn, Uranus, and Neptune.
okay.
Okay, good.
I get it now. That third time really clarified.
Okay, great. Okay, so now you want to apply this knowledge basically to the stars. So what did we learn by looking at the solar system? We learned that the planets that are further away from the sun, they feel less and less gravity because of the increased distance, and they move slower and slower. And so we have this, we realize now that the speed of the planet is related to the amount of the gravity that it feels. And the gravity depends on the mass inside of the orbit and the distance from the sun. So let's see now what will that tell us when we apply to the galaxies, okay? So what do you say over here, number 7?
Well, before watching the video, I was thinking it was the halo. But after watching the video, I realized that dark matter is distributed throughout all, and the reason that you see the light there, you know, there is stars, but the stars that are in the center don't have too much mass.
Okay, now I know that. So now it's not good that you watch the video because you have to kind of act surprised as you're going through this lecture tutorial.
Before I watched the video, my answer was the halo, the center.
Exactly. Okay, good. The central bulge.
Then I watched the video, and that's what I told you. I shouldn't watch the video before because everything changed.
Sure. So basically, okay, so it is now just by looking at this picture, because for a long time, you know, just the pictures were what we had. And so you're looking now at this spiral galaxy, and so where there is more light, there must be more stars and more mass, because we initially thought that all of the mass of the galaxy is inside of the gas, dust, and stars. So when we measure the amount of light coming from different parts of galaxy, we find that stars are concentrated in the central bulge of the galaxy. Okay, and then very spread as you move through the disk. So based on this information, where do you expect most of the mass of galaxy to be located?
The halo, central bulge.
The central bulge, the halo is something else. The halo is basically that spherical envelope kind of the galaxy. So we don't see there many stars. We only see globular clusters in the halo, but there are not too many of them, like, 100 and maybe a little bit more of globular clusters in the whole Milky Way. So when we look at the galaxy, we think most of the mass is somewhere here, right? Within this circle A, and that's the central bulge. Okay, good. And so now, question 8. So what do you say now?
A, C, B.
Oh, let me read the question.
So now you have stars A, the sun, and B. And yeah, what did you say? What would be the fastest star?
A.
And then?
C.
You mean sun?
The sun, and then B.
Very good. Very good. Because once again, as you go further away from the mass, the speeds should go down. That's what happens in the solar system. Okay. And so now it tells you over here this very important concept, rotation curves, right? And so what is the rotation curve? You have speed on the y-axis and distance on the x-axis. And it's asking you now which rotation curve best represents the relationship you described in the question 8.
Which represents the
Number 1.
Mm-hmm. Yeah, is it rotation curve number 1 or 2?
1 for our solar system.
1, very good, because in the curve 1, what do you see? That the speed decreases with the increasing distance.
Yes.
Okay, good. And so now this is now you're learning in this part. Okay, so astronomers were surprised when they saw the real rotational curve of the Milky Way galaxy. So this is the real rotational curve, and it shows you over here, it's the edge of the central bulge. So now where do you think stars A, B, and the sun would be on this rotational curve?
I place A where the arrow for H of central bulge is.
Okay, so you're saying A should be somewhere here.
Yes.
Okay, that's correct, because A is at the edge of the central bulge. Okay, and then?
I place the sun like around where the letter S of a speed is, down, like towards.
Here?
No,
Oh, here?
yes.
Okay.
But then I saw the video and I realized that was in the first place that you showed me next to the other one.
Okay, but let's just not go to the video. But when you look at this picture, here is the distance is 0 because we measure distance from the center of the galaxy. So here is the distance 0. And then if you put the star A at the edge of the bulge, and that is correct. Now, what do you see? The sun is further away, right? If you put it like where you just told me you did before you watched the video, that means you place the sun somewhere here, closer to the center of the galaxy, and that's not the case, right? So going back here, if you said that the star A is here, then sun is further away, so you have to move in this direction. So sun is somewhere here, and then the star C is going to be, or B is going to be somewhere here. Do you agree?
Yes.
Okay, good. Okay, so that would be, and so then what do you see actually about these stars? So here is now all of these questions you have to answer.
Describe how the star's orbital speeds shown in the rotation curve for the NWG are different from the orbital speeds shown in the rotation curve, which is in question 9.
They are about the same.
Yeah, very good. They're about the same. And so is that different than solar system?
Yes.
Yes, very good, because in solar system you expect them to decrease. Okay, how about question 12? You already said they're about the same, right? They move it about the same speeds. Okay, so question 13.
No. Mass is distributed at large radius beyond the stars.
Why do you say that?
1 second.
No.
No, because I see the stars in the graphic 10.
Mm-hmm.
But they are not. Like I was putting them at the beginning. They are all the same. They are close around,
Mm-hmm.
and they are not in, like in the solar system, increasing
Mm-hmm.
or decreasing.
Yes.
And the stars are distributed evenly.
In terms of speeds, that's what you mean, right? They all have the same speeds.
Yes.
And so what does that tell us? So what does that tell us about
The mass is distributed. The stars are distributed all over towards the arms, the disk.
Well, okay. I think maybe it's easier to first answer question 14 and then go back to 13. So, Anna, are you talking?
Yeah, I'm trying to talk, but I'm still confused on 13, so that's why I'm skipping to 14.
So 14 is maybe easier. So based on this real rotational curve.
The force felt by the Milky Way galaxy stars is greater than I expected.
Yes, very good. So how do you know that? Because the speeds are related to the force of gravity, right? The fact that the speeds are all the same, that they don't go down, they don't decrease, tells you that all of these stars in a way feel the same force. So how is that possible? Because you do know that the distance is changing. So because of the changing distance, the force of gravity should weaken. The fact that it's not, what does that tell you? What's happening in the Milky Way galaxy?
That there is the force there must be a force that is pulling
on all the gravity.
Well, but it's the force of gravity always keeps things. Let's say these stars, when you think about them, why do they go around the Milky Way galaxy? Because force of gravity keeps them in their orbits, right, and keeps them circling basically around the center of the galaxy. So the force of gravity depends only on two things, right? That's what you learn in the first part of this lecture tutorial. One thing is the distance, how far these stars are from the center of the galaxy. And the second thing is like how much mass is inside of the orbit of the star. So the fact that the force is not going down and that these speeds are flat, what does that tell you?
Well, that's what I'm not sure what I watched. The dark matter is evenly distributed throughout the galaxy.
Yes.
Further from the center, increase high orbital velocities, which keeps the stars going around the galaxy.
I agree. So, so what you see over here is, once again, I don't know, I think you're reading from the notes, but I just want you to think about this question and these two graphs now, what you're seeing. So what you're seeing on those flat rotational curves is that the speeds of the stars remain constant or flat at, large range of distances from the center of the galaxy. Okay. So you do now know that, how is that possible? That speed is related to the force of gravity. And the fact that the speeds are not dropping down tells you that the gravity is not weakening down. So, but the distance is increasing. So based on distance, you would expect that the force of gravity would go down or decrease. The fact that it's not tells you then that there is more mass than we can see, right? Because we know that the force of gravity depends both on mass inside of the orbit of a star and the distance. And so they have the same speeds, even though there are different distances from the center of the galaxy, because as we move away from the center of the galaxy, there are less and less stars, but there is more and more, like some other type of mass, which we call the dark matter, because it does not emit the light, right? We don't see it, but we actually know that it's there because of its gravitational influence of these stars.
Yes, and in your lecture, that was what Vera Rubin was trying to.
Exactly. Vera Rubin showed that actually in 20-30 galaxies that she measured, the speeds of stars, the stars behave the same in every single galaxy. When you would expect speeds of stars to go down, they don't go down, they remain flat, which tells you that there is more force of gravity than what we can see by just looking at stars. And so that, people before called it missing mass, and now we call it the dark mass or dark matter, because that is that mass that is providing those stars to be locked inside of the galaxy and have those high speeds.
Okay. Yeah. I'm getting it together pretty kind of well, but I think I just need to reread again.
Yes. So this is really the hardest part in this chapter, or in this week, actually.
I think I got it. I just lost it. Is just what happened. Because that's like the first time I read something like that. So. So the reasoning, the using analogy with the solar system is really good, because you can understand how these planets are moving slower and slower as you move away from the sun. And so the analogy is that when you look at the galaxy, most of the mass is inside of the bulge, like most of the mass in the solar system is in the sun. And so what you would expect is that stars also, the further away you go from the bulge, they would move slower and slower. That's based on what we see. The fact that the speeds are not going down, but they remain flat, tells you that there is more gravity than, what is revealed by the stars. And so that component that provides the gravity, but it does not emit the light, is the dark matter. Okay, good. And so here you have now these two students. They're going to summarize that. So you can both take your time, read this, and then tell me which student is right. Okay, don't give me the answer yet.
Okay, I'll be quiet.
I have the answer, but I wait
for the answer yet.
Yeah, that's what I say. Wait for you.
Hold on. Oh, automatically student 1 wins.
Yeah, I know. Student 2 is just talking these unrelated sentences, right?
Yeah.
Okay, good. Raoushda, you agree?
Yes, I had the same.
Okay, good. So student 1 summarizes nicely kind of about this worksheet.
That's a write down.
Okay, good. Okay, let's now go. We have 2 more questions, okay? They're also like summary type questions. So what do you say, Raoushda, number 16?
Well, that the dark matter distributes evenly, and dark matter reveals itself by the influence of its gravity. That's how really we know that it's there.
Mm-hmm. Mm-hmm. I agree with you. Okay. Okay. Anna, you want to give your summary?
Yeah. I wanted to just say, I guess they were able to detect them just like through the gravitational lensing with the whole photons, and then just
But not in our galaxy. In our galaxy, nothing with the gravitational lensing right now. So astronomers initially thought there was more mass in the center of the galaxy than in the rest of the galaxy because there is more light coming from the center. So that's correct, more light coming from the center. Describe how astronomers' observations show these initial ideas are wrong. So what type of observations showed us that these initial ideas are wrong? And that's what this worksheet is about, kind of. What do you say, Rojda? What observations showed us that these initial ideas are wrong?
Same one, Vera Rubin in 1970, she did 60 confirmations after she noticed that the stars were moving at the same speed.
Okay, very good. So this fact that the stars are moving at the same speeds or, flat rotational curves that you see for the motion of the stars throughout the galaxy, that showed us that these initial ideas are wrong because they indicate that there is more mass in the galaxy than what emits the light.
So they measured the speeds of the galaxy.
Stars, speed of the stars in the galaxy. Uh-huh.
Okay.
Good. Okay. So number 17.
Before we move to 17, all this light coming from the center is coming from where? From the stars?
Yes, exactly.
The amount of stars is because, what I'm thinking is in the center, this is talking about the central bulge?
Yes.
Okay. Because I was thinking about the halo and, the stars don't have mass.
Yes, no, when you look at our galaxy, the central bulge has the highest density. There is a supermassive black hole, right? 4 million solar masses. And then you have extremely high concentration or density of the stars over there. They're like, thousands of stars. Let's say from the sun to the nearest star is 4 light years, right? And there is nothing in those 4 light years. It's completely empty in terms of stars. If you look at the same amount of space in the central bulge, you're going to have thousands of stars, okay? So the density of stars is much higher in the central bulge. And if you have more stars, there is more light coming from there. And so there is more mass over there that emits the light. So that's that idea. And then when you talk about the spiral arms, spiral arms, they're important because they have gas and dust, so they can form new stars. That's where the star formation happens. But the density of stars is not as high as it is in the bulge. It's much lower. We are in the disk between the spiral arms, right? And then that there are not too many stars around us.
Thank you.
And then the halo is, it's not completely empty. Obviously, they're globular clusters, but you have even much more
mass stars and less stars.
Okay, good. So how about question 17?
The answer to me is yes.
Yes.
There is by the influence of its gravity.
Okay, good.
Oh my God, that was good.
Okay, good. So yes, there is way more mass than what we can see. So did you actually, in the lecture notes, I have this slide that says how much of the mass is in the normal matter or the matter that emits the light, such as stars, gas, and dust, and how much of the mass of our galaxy is in the dark matter component. Do you know what's the ratio between them?
I think yes. You have a thing that says galaxy, dark matter is 90%.
Yes, very good.
Matter is 10%.
Yes, very good, Rojda. Excellent job.
I didn't look at the
Okay, good. Okay, and that's going to be, as we move on, that's going to be generally true for galaxies. So most of their mass is going to be in the dark component.
I think just my recommendation for someone that had not done the homework is watch your lecture first and the other video they want to do after, because it helps.
Or reading the book.
And reading the book, I agree. I think Yes, all of those.
To do it again. I
It was
did it
very good.
before.
The lecture was very easy to understand.
Okay, good.
And that video, the video that I shouldn't watch, but that was very helpful too.
Okay,
that's
great.
That one. Yes.
Okay, do you have any other questions then related to this week?
They're welcome.
No. It was good.
Yeah, the video flat rotation curves. That was very good.
Okay, so are we all set then for tonight?
Thank you. Yes, I am.
Great.
You will be published pretty soon on the YouTube, so.
Oh yeah. Thank you.
Okay, see you.
Thank you very much for today. Thank you.
You're very welcome. Thank you for stopping by and see you the next week.
Yes.
Bye, teacher. Bye, Anna.
Bye, Anna. Bye, Rojda.
Bye.